Hello everyone, today I'll present the LPOD paper, which is published in the Big Data Congress in 2019 years old. LPOD is short for a local path-based optimized scheduling algorithm for deadline-constrained big data workflows in the cloud. First, I'll give the overview of this presentation. First, I'll give the introduction, then the problem, then the previous approaches and the limitations. Then I will present the proposed approach. After this part, I will show the experiment results. Then I will give the conclusions, then I will give the future works. Here is the introduction. As we all know that workflow scheduling is the NP-complete problem, which means that we cannot find an ideal solution in the polynomial time. Also, the workflow scheduling is the most challenging module in any kind of workflow management systems. Not only in the big data company or the research facilities. They always use a workflow management system to do different tasks. The cloud computing comes with a lot of benefits, such as the elasticity, the pay-price model, and also the cloud computing can provide unlimited capacity of the computing resources. So in this case, the cloud computing can be suited for the exploratory scientific computing applications. So we can just benefit from the cloud computing to do a lot of research issues. During the introduction, I explained the workflow scheduling problem, and how about the deadline constrained workflow scheduling problem? It means that a specific workflow should be finished before a deadline. We call it delta. Here is the dummy workflow, and here is the cloud computing resources. We call EC2 instances, and we want to make sure that dummy workflow can be finished before a fixed deadline in the EC2. Then we can generate a workflow schedule with the minimized memory cost. So this is previous approaches. Some people assign a whole partial critical path to a single VM instance to minimize the data transfer time between the consecutive tasks. And some other researchers do a pre-processing of the workflow graph and combine the pipeline tasks into a single task, and then assign this combined mega task into one single VM instance. These two approaches are very similar, but the difference is the second one is just use linear structure, and the first one is use the critical path. And some other researchers use a two-stage procedure to minimize the execution cost and the workflow mix spin at the same time, which is extending from the heft algorithm. So let's talk about the limitation of the previous approaches. So the first one is they don't fully consider the important characteristic of the cloud computing environment, such as the starting time of each virtual machine. It's not always true that the virtual machine can be used immediately after this virtual machine is provisioned. The second one is runtime scheduling strategy may violate the deadline constraint. In the real case, sometimes we submit some task and we follow the workflow schedule, but the result is this schedule cannot meet deadline. Even in the theoretical, it can within the deadline, but in the real case, it may violate the deadline constraint. And last one is the hyperparameter is very hard to choose during the workflow scheduling, such as how many virtual machine do we need to use for each kind of virtual machine type. So we want to propose our motivation, and can we assign a path to the multiple virtual machine instance in a search for the better result solution? The answer is yes. So based on this motivation, and we also have some challenges. The first one is the cloud heterogeneous environment. It means given a workflow, how to decide the appropriate virtual machine types from 182 virtual machine types, and how to decide the number of virtual machine instances for each kind of virtual machine type. The second one is the heuristic approach. Due to the problem belonging to the NP-complete problem, how do we use the heuristic strategy to find a good solution in the polynomial type? So here is the contribution of our research. We propose a path-based workflow scheduling algorithm, which generates the workflow schedule of minimizing the execution cost on Amazon EC2. And the proposed algorithm is implemented and integrated into a real popular workflow system, which is called DATAVIEW. And we also conducted some experiment, and the results showed that LPOD outperforms the state-of-art algorithms, which are ICPCB and SGS E2C2D. Then we enter into the notation of these papers. The first one is the cloud computing environment C, and we can model the cloud computing environment as a non-tuple, including the VMT, VMC, vprice, VMI type, DTR, dprice, both delay. So the VMT is the set of virtual machine types in the environment, and the VMC is the VM capacity function, and the vprice is the VM price function. VMI is set of VM instances, type is the type function, DTR is data transfer rate function, dprice is the data transfer price function. Both delay is the delay time for a VM instance before it becomes available after being provisioned. Then we introduce the big data workflow W, which is modeled as a 4-tuple, including the TD, T-size, D-size. T is a set of tasks, and D is a set of data dependency edges between tasks. And T-size is a task size function, D-size is a data transfer price function. Now we can define the workflow graph G, which can be formalized as a 5-tuple, the TD, TE, DTT, DTC. The T will be included the T entry, T exit. These two tasks are dummy tasks. So it means that this task, the execution time of these two tasks in any kind of virtual machine types are 0. And in this case, we want to make sure that for any kind of workflow, we can only have one entry task and one exit task. And for the D, and we will add one edge from the D, every edge from the D entry to the first task in the workflow, and every edge to the last task in the workflow to the exit task. Then D will include all the edges. The ET is the task execution time function. ET bars is the average task execution time function, and the DTT is the data transfer time function, and the DTT bar is the data transfer time average data transfer time function, and DTC is the data transfer mandatory cost function, And in this paper, we assume that this value is 0 because we just use one zone. And then we introduce the workflow schedules. Given a cloud computing environment C and workflow W, workflow schedule is modeled as a 7-tuple which called sh, including the T, the VMI, M, ST, FT, PRO, deprov. The T is the settle task in the workflow, and VMI is see the difference is not the settle tasks in the workflow graph. It's settle tasks in workflow W. VMI is set of VM instance in C, and M is a task assignment function. So the input is one task, and output is a VM instance. And SDT is an extra start time function. FTA is an extra finish time function. Prov is a VM instance provisioning time function. Deprov is a VM instance deprovisioning time function. With the above notations, and we can calculate the workflow cost, which we noted as WC. And given a workflow schedule Sh, the total execution time and cost of Sh in the cloud computing environment C is defined as we can calculate how many billing cycles for each kind of virtual machine type, and then we multiply by the virtual machine type price, and we sum all the values. After we have the total workflow cost WC, and we can define the optimal workflow schedule, which called the OPT. And given workflow W, the cloud computing environment C, and a deadline delta, the optimal workflow schedule is defined. We can we want to minimize the workflow cost by giving the Sh, and with one constraint is the extra finish time of the exit task should be smaller than the deadline delta. This is the optimal workflow schedule. And here is the whole structure of the LPOD approach, which takes two inputs. The first one is workflow graph, and the second one is deadline. And the output is a workflow schedule Sh. And so as we can see that it includes 4 main steps. The first step is calculate the priority value for each task, and step 2 is assign the EST time and last finish time for every task. And step 3 is the construct the partial passes, and the step 4 is the passes assignment. Here is the pseudocode of the LPOD algorithm. So you can see the whole picture of the algorithm 1. This is the input and this is the output. First, we assign a non-value to the Sh, and then we just calculate the priority rank for all the tasks in G in an descending order. Then we calculate the earliest time for every task. Then we calculate last finish time for every task. Then we find all the partial passes based on the priority values. Then we just call the pass assignment function. But how do we calculate the priority value? And for this is the formula how we can calculate the priority value. If the T is equal to T exit, so we just assign the average execution time of this task. If t is not equal to the exit task, so we will try to get to the biggest value of the average data transfer time between this task to the children task, and plus by the priority value of the children task. Then we go to the notation of the earliest start time, and first we want to define another notation which is execution time start. It means that so if the task is already mapped, it's here. So it means that one task is already mapped to a virtual machine type, then we can use the execution time for this task in this kind of virtual machine type. But if the task is not mapped yet, so we should use the minimum execution time for this kind of task. Then we can base on this notation, and we can get the EST for every task. So this means the parent task of the TI. So we start from the T entry task, and we every time we want to get the max value of the parent task, and plus by the ET start time of the parent task, and plus by the average data transfer time of the parent task to the children task. Also, we have, based on the same logic of the last finish time, so we also define another the notation ET star, but the difference is last finish time is start from the exit task. So we defined the last finish time of the exit task is equal to the deadline delta. Then we start from the exit task, then we traverse back to the entry task by this notation. Then we see how do we find all the partial critical passes. The input is a sorted task list. Then the output is a pass list PP. First we make the PP is empty, and for every task in the sorted task list, and we defined a temporary list which is TP, and since the T list is already in descending order, so we add the first task, and then we remove the first task of the T list, and then in the where statement we want to select the first assigned task of the TI. Then we add the TI to the CP and remove it. So when this task has no children, and we can add the CP to the PP, and at last we return the PP. So this algorithm constructed the partial critical passes based on the priority rank for each task. Start from the exit task recursively Okay, so this is the past assignment. So here from the line 1 to the line 16, so we just want to find the prefix of one pass can be assigned to the free virtual machine instance. So we have several conditions. The first condition is the virtual machine instance available time should be smaller than the earlier start time of this task, and also the virtual machine instance left time should be larger than the execution time of this task in this virtual machine type. And also we need to make sure that last finish time should be bigger than the execution time. If all these constraints can be met, so then we can just update the workflow schedule. So the LG is the prefix index, and the found is the indicator that we can find this kind of free instance. So if the found is false, so we can just break. We continue to find an then we call when we find the LG value, and we can assign the remaining path to a new virtual machine instance. Then we can update the EST for every task in this path, and we just assign the actual start time to the EST and actual finish time to last finish time. Then we updated the EST for all the successors of TI according to the notation, and we updated the last finish time for all the predecessors of the TJ. So here is a past assignment. So in here, it means that for all the tasks in this path will assigned to the new virtual machine instances. But how we can do it? So we will use the temporary TV, and which is a table, and from the line 2 to 7, and we always assign the first task to a new VM instance. Then we loop for each virtual machine types, and we create a new tuple, and we give a ID for this tuple, and then we assign the element T is equal to the current task, and the element TST is equal to the boot delay, and the element TFT is calculated based on the notation, and the accumulated cost is also calculated based on the notation 7, and this current billing left time is calculated by the notation 20, and also we have the reference index, which is none, and also we need to have the max age value element, which is calculated by the equation 23, and also the VM type need also to be installed. At last, we need to do a judgment that if the TFT is smaller than the last finish time. So in this case, we can keep this temporary result to the TB. And from the T8 to 18, and we just do a temporarily assign a task to the same VM hosting the previous or not based on the previous task assignment. So we start from the second task to the lesser task, and then we just based on the previous tuples in the of the previous task. Then we need to check. So if the current new tuple the element VM type element is equal to the previous element, and we can update all the tuple elements. And if it's not the same element, and we can also update all the elements in the tuple. But the most important thing is line 20. Also, we need to make sure that all the last finish time should be smaller than the TFT. So in this point, and we just create a temporary table, installed all the informations. The task can be assigned to different kind of virtual machine, and we also have the accumulate cost, right? And then so we want to make sure that the cost is a minimum one, right? So we can just select all the candidates by having the minimum accumulate cost, which is 97. So then we can just select one. We can identify one of the minimum cost by assign all the tasks in a path. So in this case, and we want to traverse back to find the VM instances with assigning these tasks. Then the line 20, we will update the shi based on each attribute of the last task in the path P, and we can, since the TP has all the informations, and we just need to update this kind of information to the shi. Then line 24 to 26, it means that if the virtual machine types in the pre-ET and the CT are of the same time, the provision time of the time instance in the PIT need to be updated. Also, from the line 28 to 41, so when the VM type in the pre-ET and CT are different, the provision time of the two virtual machine type need to be updated sequentially. Here is the line 44 is a special case that there is only one task in the P. So in this case, I just show you how the algorithm for works. So here is the experiment settings. In this experiment, we use the Montage and LIGO workflow structures, which are simulated in the DATAVIEW, and the task sets are simulated by the bubble sorting with different data size. and we use the three kind of virtual machine types in Amazon T2 micro, T2 large, and T2 extra large to use to execute this workflow. And the average task execution time and data transfer time is calculated height before the experiment. And we use the evaluation metric C-score to assess the performance of the workflow schedule generated by each algorithm. Here we use the baseline, which is 0.5, and if the make spin is smaller than the deadline delta, and we can just give the reward. So we can use the max cost manners the cost divided by max cost times 0.05. But if the mix span is bigger than the delta, and we will give a punishment. Then we will define the deadline distribution, and which is based on the fastest workflow finish time. It means that we'll assign all the tasks into the fastest virtual machines. So this is the formulation of the deadline, and the lambda range from this 1 to 15 with the step length of the 0.5. So here is the 10 milliseconds for the LIGO, as you can see here. So when the deadline factor is about 10, so the C score is bigger than 0.5, and so the green color is the LPOD. So you can see that LPOD is better than the two other algorithms. And this is the 10 milliseconds for the montage, and so this one little, so this one is maybe the deadline factor is 0.5, the C score should be above the 0.5, and this is the 30 milliseconds for the LIGO, and as you can see here, it's the same, and but this is the 6 spinning cycle, 6 spinning cycle for the montage. As you can see here, so if the spinning cycle is bigger, so the performance is bigger than the smaller one. So here is the conclusion. So we proposed a new workflow scaling algorithm, LPOD, and we can successfully find optimal schedule for each particular path from the workflow graph G. Also, its permanent result demonstrates the performance are better than the state-of-art algorithm, the SCPCP and the SGS E2C2D. So the future work, first we would like to explore the partial path assignment to generate better schedule, and we will explore the possibility to utilize the provenance information to retrieve the average task execution time and data transfer time automatically, and the workflow executors to be more reliable to follow the generated schedule. So we want to avoid the influence of the system issues. Then finally, we want to combine the time status to update the workflow schedule in time. Thank you. If you have any question and not clear, and you can email me. Thank you.